The atomic bomb is the most complex and consequential object ever produced by human ingenuity. It is not just a weapon, but the final result of an industrial chain that pushes the limits of physics, chemistry, and engineering. To transform inert rocks buried in the ground into a device capable of unleashing the power of the stars, it is necessary to mobilize resources on a scale that few countries in history have managed to achieve. Forget the image of the lone scientist in a laboratory. The construction of these artifacts is a titanic undertaking, involving factories the size of cities, energy consumption equivalent to that of entire nations, and mechanical precision. Where an error as thin as a strand of hair can mean the difference between an apocalyptic detonation and a useless piece of metal. Let's open the doors to this invisible industry and understand step by step how absolute power is manufactured. The journey to build any nuclear weapon begins on Earth. The fundamental ingredient for the first generation of bombs, those based on splitting atoms, is uranium. Although it's not a particularly rare metal, uranium is spread throughout the Earth's crust in low concentrations. The industrial process begins with large-scale mining, removing tons of rock to extract the raw ore. This material is taken to plants, where it is crushed in giant mills and subjected to acidic chemical baths. The goal is to separate the uranium from the waste rock, resulting in a concentrated powder with an intense yellow color, known worldwide as yellowcake or yellowcake. However, the uranium that comes out of the mine has a fundamental problem for nuclear engineers. It is mostly made up of uranium-238 atoms, which are very stable and are not suitable for creating a rapid explosion. What we are looking for is uranium-235, a slightly lighter and much more unstable sibling, which makes up less than 1 atom out of every 100 found in nature. The industrial challenge here is to separate these two types, which are chemically identical. The solution found was the brute force of physics. The yellow cake is transformed into a highly corrosive and dangerous gas, uranium hexafluoride. This gas is injected into vast industrial complexes filled with centrifuges. These machines are vertical tubes that spin at supersonic speeds. The centrifugal force pushes the heavier atoms to the walls, while the lighter and desired atoms tend to stay in the center. Parallel to the uranium path, the nuclear industry developed a route to obtain explosive fuel, plutonium. This element practically does not exist in nature, being found only in very small quantities mixed with uranium deposits. In other words, we can say that it is a man-made metal created to be manufactured. The common uranium, the one that was discarded in the enrichment process, is placed inside powerful nuclear reactors. Inside, it is bombarded by neutrons for long periods, and this constant bombardment changes the atomic structure of the uranium, converting it into plutonium-239. The challenge with plutonium arises when it comes time to remove it from the reactor. The irradiated fuel is one of the most lethal substances on the planet, emitting intense radiation and heat. The separation of plutonium from the rest of the nuclear waste needs to be done in facilities called chemical canyons, massive concrete buildings where no human can enter. The final result is a silvery heavy metal, warm to the touch, ready to be shaped into the heart of a bomb. With the fuels ready, enriched uranium or plutonium, precision engineering comes into play to assemble the fission device. The goal is to create a critical mass, that is, to bring together enough material in a small enough space so that the chain reaction can sustain itself. There are two designs. For the first one, used only with uranium, it's the gun-type model. It's a robust and relatively simple system. Inside a strong steel tube, a piece of uranium shaped like a projectile is fired by a conventional explosive against a second piece of uranium, which serves as the target. When the two meet at high speed, they form the critical mass, and the nuclear explosion occurs instantly. For plutonium, however, the gun method does not work because the material is too reactive and would explode prematurely. For it, the complex implosion method was developed. A hollow or solid sphere of plutonium, usually about the size of an orange, is surrounded by a puzzle of high-powered conventional explosives, shaped with millimeter precision. The secret is to make all these explosives detonate at the exact same instant, with nanosecond precision. This creates a spherical shock wave that travels inward, compressing the plutonium until it reaches an absurd density. At that moment of maximum compression, a small device at the center, called the initiator, releases a burst of neutrons to ignite the chain reaction with total efficiency. Up to this point, we've described fission bombs, which split heavy atoms. But the history of the nuclear industry didn't stop there. The search for even greater power led to the development of the hydrogen bomb, or thermonuclear bomb. This device works on the opposite principle. Instead of splitting heavy atoms, it fuses light atoms, the same process that generates the sun's energy. However, to fuse hydrogen atoms here on Earth, unimaginable temperatures and pressures are required, which no conventional machine can produce. The industrial solution for the hydrogen bomb was to use a fission bomb made of uranium or plutonium as the trigger to ignite the fusion fuel. A modern H-bomb is actually a two-stage device, assembled within the same casing. At the top is the primary fission bomb, and below it is the secondary fusion fuel, usually a solid compound called deuterine. All of this is enclosed in a casing made of dense materials, such as natural uranium. The operation is a sequence of events that lasts fractions of a second. First, the conventional explosives detonate the primary fission bomb. This explosion releases an immense amount of X-rays, which travel at the speed of light and fill the space inside the bomb's casing. Before the physical shockwave destroys everything, these X-rays violently heat and compress the secondary fusion fuel. Under this extreme pressure and heat, the hydrogen atoms in the lithium deuteride begin to fuse, releasing energy hundreds or thousands of times greater than that of the original fission bomb. The result of all this industrial effort, when released, is the instant transformation of solid matter into radiant energy. At the center of the detonation, temperatures exceed tens of millions of degrees Celsius. The air is instantly transformed into plasma, creating a fireball that expands at supersonic speeds, generating a shock wave capable of leveling cities. In addition to the thermal and mechanical destruction, there is the invisible legacy of radiation. The explosion releases a flood of neutrons and gamma rays, and the subsequent mushroom cloud sucks up tons of debris from the surface, mixing them with the radioactive waste from fission and fusion. This material returns to Earth as radioactive fallout, contaminating the environment for decades or centuries. And that was today's video. Please like and subscribe to the channel.